Okay, welcome back to the second part of this standard scores segment of the video lectures. When we left off, we had stopped with this slide on norm reference tests and norm reference interpretations of scores. And what I want to do is to start out with just a basic definition. Norm reference is just that. You are being compared to other people. Unlike the criterion reference that we just talked about, where you're being compared to specific outcomes that you can or you can't do a particular performance. Norm referenced assessments only measure how well you did compared to other people in the norm group or other people in the group of folks that took the test when you did. So a norm group could be from a national test, or you could also compare the performance of students, say, within a class. We typically don't do this. If you ever heard of teachers who grade on the curve, that's exactly what they're doing. So it's the student score relative to other students or other folks in a norm group. We have to know who the norm group is. Who are you being compared to? It's very important. And then finally, there isn't an issue with the level of mastery. It's just about how well you did compared to the other people that took the test. So when we complete a norm referenced assessment, what's generated are a set of derived scores. We start with a raw score and we convert those into numbers that have a meaning within a particular comparison group or a particular norm reference group. So we need to have derived scores because simple rankings have limited value. Knowing that you are the worst student or the best student is useful, and that's really ultimately what the percentile ranking tells us. But it doesn't allow us to transfer between different groups. So by converting your actual raw score into a derived score, which is based on a standard deviation unit, typically anyway, we can make some inferences, or we can have some understanding that we can't have just based off your percentile ranking. Some of the most common types of derived scores are grade equivalents, percentiles, and standard scores. And they're pretty easy to calculate, these, and conversion tables are usually provided to give you different kinds of scores. So we're going to look at several of these in turn in just a moment. As I mentioned a moment ago, most of these are standard scores. For example, T-scores or National Curve Equivalent scores, standard age scores. They're all based on the same logic of using the normal curve and your position of performance relative to the average performance of the group you're being compared to. If that doesn't make sense, we'll talk about it more in a moment. There are other kinds of developmental scales that we sometimes generate other than grade equivalents. For example, sometimes age equivalent scores, but they work on the same basic premise. One of the things that we also run into from time to time when we look at norm reference assessments are things called expectancy tables. For example, we might have a two-way chart that shows how often students with each score band, say on the SAT, wind up doing with their GPA as freshmen in college. So, for example, we could say that 75% of students who achieve over a 600 in mathematics wind up pulling at least a 2.5 in their freshman year of college. Now, this is an expectancy table. It tells us what the likelihood is of an outcome based on some kind of predictor score. And so norm reference assessments are often used in this manner to make predictions about some future performance. We don't need any norms to do this particular process, and I mention this because it is one of the uses that norm reference assessments are commonly pulled into play for. For example, if you're a college and you set a minimum criterion for entrance, for example, let's say that your minimum entrance SAT score for quantitative and verbal, not with the writing included, let's say that combined it's say 1200. That's based on the premise that students who earn below a 1200 fail at a disproportionately high rate. That's an expectancy table. And so that's why colleges or universities often will set minimum criteria for the SAT, because what they're trying to do is, of course, reduce the number of students who fail. So grade equivalent scores are one of the most common kinds of scores. They're also one of the most dangerous kinds of scores. Typically what I'll do is I'll ask in the course, and I'll say, how many of you know what a grade equivalent score is? How many of you can provide me with an accurate definition? So I'll pause for a second, and I'd like you to write down your own definition. And so pause the video right now, and go ahead and jot down your own definition of what you think a grade equivalent score is. Okay, so let's see if what you wrote down matches what a grade equivalent actually tells us. Grade equivalent score is the grade level at which the typical student obtains the raw score. Well, what does that mean? So we often hear that the fourth grade student had the same raw score that was the average for students in the grade 5.6 in some average school. Well, you're probably still sitting there scratching your head saying, well, what does that mean? So imagine this for a moment. If you're a fourth grader and you take the fourth grade test, we'll say maybe the Metropolitan Achievement Test. And it's a basic achievement test that's given across the country. It's not used as much anymore as it once was. But you take this test, and we'll say that you complete it for the mathematics portion, and you earn a score. Your score is compared to all of the other fourth graders that took that test. So if you're a fourth grader and you completed the test, and let's say that you got 47 items correct, we find out that as a fourth grader, you did better than the average fourth grader. The average fourth grader maybe only got 40 items correct. You, on the other hand, got 47 items correct. And so you earned the same average number of raw items correct as students not in the fourth grade, but actually students in the fifth grade who were given that fourth grade test to take. So when a test is developed, it's not given just to the grade level for which it's designed. It's typically given to several grade levels above and below to help to characterize the performance of students who are slightly older and students who are slightly younger, so that we can get a sense of what is the grade equivalent score that would be associated with the score that this child received. So that 47 turns out to be the same average score as the average score for the fifth graders. So I'm going to jump out of this, and I'm going to show you a little demo. Okay, so I'm going to try to demo this, so we'll see how this goes. So if we think about getting the right tool here, this is, of course, our bell curve or a normal distribution. It's a hypothetical distribution, and we know that the average person or the average student, their score falls right here, right in this midpoint line, okay, where half of the students are above and half of the students, or the folks taking the test, are below. So for our grade equivalent discussion, I want you to imagine for a moment that we have a student that has scored our 47, right? We just talked about him. And so here is his score right here at this level. And there are all of these other students that are at this level that also got this score. And we see that the majority of students in fourth grade, okay, so remember this is fourth grade, this is the distribution for those fourth graders. And let's see how good my writing is with my stylus here. Our target student scored here. The raw score was a 47. And we see that that's approximately 1 standard deviation above the mean. All right, so you may want to come back to this demo portion of this for some of the other slides as we're thinking about different kinds of standard scores. So I'm just going to kind of explain a variety of standard scores here. I'm going to go back over them in the slides as we go through t-scores and z-scores, but I want to go through here. The z-score is right here. It's, in this case, +1. And this is equivalent to a t-score of 60, okay? Because our t-score in the case of +1 is 50, which is our midpoint right here. And each standard deviation unit is an increase of 10 points. So 50 t-score, 60 t-score, 70 z-score, 80 z-score. Okay. Conversely, of course, 40 z-score, 30 z-score, 20 z-score. Now, our child got a raw score. Okay. This, remember, is our raw score of 47. That puts them at a t-score of 60. It puts them at a z-score of +1. It puts them at approximately the 84th percentile. Okay, we'll talk about what that is in a little bit. And we're talking right now about a grade equivalent score. And what we find is, in the case of this child who earned the raw score of 47, that they had a grade equivalent, remember I said of, I think, 5.6. So grade equivalent equals, excuse my writing, I've got to figure out a better technology in the future to use. So grade equivalent equals 5.6 here, right? What we see is that this is determined because if we looked at the distribution of 5th graders who took this 4th grade test, we would see a distribution that looks something like this. So I'm going to make a miniaturized version of this distribution right here. All right, so pretend that that's the highest point right here. I didn't quite make it. But right here was actually our peak. All right, so if we were to imagine the peak actually being right there. And our student in 4th grade got the same average score as the mean score for 5th graders in their 6th month of school. So a grade equivalent score is not saying that our 4th grader should be in the 5th grade. It's saying that our 4th grader got the same average score as the average 5th grader in the 6th month of school. Conversely, let's say that we had another student who scored down here. They got a raw score of, if this was 47, oh, I don't know. We'll make up a number. You see how the raw score is pretty arbitrary. It's about relative performance. We'll say that the raw score was 31. That raw score of 31, we find, puts them 1 standard deviation below the mean. That's a z-score of -1. Okay, so quick question. T-score is what? 40, right? So T is 40. And their percentile rank is going to be roughly the 16th percentile. Maybe not exactly, but roughly the 16th percentile. 15.87, I think. So here's our second student. Okay, so student 1, student 2. And if we were to look at, let's say that this actually equates to some 2nd graders. Now, just because it's the same distance below as this is above, and just because this is 4th graders, or 5th graders, excuse me, that are about 1 standard deviation above, that doesn't mean that it's going to be 3rd graders who are 1 standard deviation below. It doesn't work that way. Grade equivalents are non-equal interval scales. So if we look here, we might see that this actually is the peak not for 3rd graders, but that was actually the mean score for 2nd graders. All right, so I know this is a mess now, but as hopefully you've gone through this, you can go back through and think about what our different markings, what my different scribbles on the screen here stand for. So when you hear someone talk about a grade equivalent score, this is what it means. So go back to the definition that you wrote down. Does this match up with your definition? If it does, that's great. You're one of the few, at least in my experience teaching this class. If it doesn't, don't feel bad. Most people don't really understand what a grade equivalent score is. I will put a footnote that if we were to take this whole discussion and we were trying to change grade equivalence to age equivalence, this is exactly the same methodology that's used to calculate age equivalent scores. So it's the same thing, same process, age equivalent, grade equivalent. They don't stand for what grade the kid should be in. Instead, they stand for how well your child or a child did, and whether or not the score that they got was the same as the average score that children in another grade received on that same fourth grade assessment, or whatever grade you're speaking of. Okay, so let's go and we will reset this. So remember our discussion, and if you've got questions, don't hesitate to contact me. This is oftentimes one of the things that people find to be more confusing or more difficult to understand. So I'm hoping that this little demo is going to be helpful. Okay, so as you might have guessed, grade equivalents are widely misinterpreted, and I do mean very widely. Don't confuse these with standards that all students should attain. It's not an estimate, again, of what grade the child should be placed in. You shouldn't expect that all students gain one grade equivalent each year, as it's not necessarily a realistic goal, and student learning doesn't necessarily happen in a linear fashion like that. Finally, on this page, don't assume that your units are equal at different parts of the scale. So as I showed on my demo, one standard deviation above might have been going up one grade in grade equivalence, but one standard deviation below was actually 2 grade equivalents below. So it's very important that you understand the way that this is calculated so that when you look at these, you'll certainly interpret them with a grain of salt. Don't assume that the scores on different tests are comparable. For example, different publishers test fuller ranges of students than others. So in the example I just showed you, I implied that they had given this test to students as young as 2nd grade and as old as 5th grade. In fact, it might have been students as young as 1st grade and students as old as 8th grade. Or it could have been that the test publisher gave it to students as young as 4th grade and as old as, young as 3rd grade and as old as 5th grade, 1 grade below, 1 grade above. But what they did was they were extrapolating the scores for younger grades and older grades. So essentially they were just kind of creating a trajectory, and they were saying, well, based on this pattern that we see so far, if the student were another year older, if the trajectory was to remain, say, equal or linear or the same curvilinear fashion, that we would expect the student to have achieved at X or Y level. And so they make a prediction, but they didn't actually measure it with a real norm group. Okay, so the cautions again then, don't interpret the extreme scores that you might get. When you get a child who is in 4th grade and they get a 12th grade reading level, certainly doesn't mean they should be headed to high school the next year. Recall again what a grade equivalent score is, how it's calculated, and you'll be far more cautious as you share these kinds of scores with parents or with other folks. And you'll be far more knowledgeable and confident in being able to say what a child's relative performance is. So there are some useful features of grade equivalent scores. One of them that I think is the best is to look at growth over time. Sometimes we have children who are performing below the expected level in a particular grade. So let's say that we have a 4th grader. He comes in and initially he's testing with a grade equivalent in the 3rd grade. And so we provide that child with a significant kind of intervention, we'll say, in reading. And we see over the course of the year that they've grown in their grade equivalent. They started out at, say, 3.2 as a 4th grader. And by the end of the 4th grade year, maybe they've partially caught up. Maybe they're at a 4.2. So they've gained a whole year. They're still behind their peers. At the end of 4th grade, they should be at a 4.9 or 10 or 12, or depending on whether it's a fractional grade equivalent or it's a years and a grade and month kind of grade equivalent. So even though they might not have completely caught up with their peers, they might not be average, they've made relative gains, and you can see that through the change in grade equivalent scores. They're very problematic for interpreting scores across tests. You certainly can't compare the grade equivalent on one test to the grade equivalent or age equivalent on another. Their inequality in the grade units is really problematic in terms of interpretation. You can't really say that increasing one grade equivalent on a test is the same as really increasing one grade in terms of actual underlying skills. So hopefully you'll look at grade equivalents and say, well, those are very nice, but we're going to use something else. The something else that you might want to consider using is percentile ranking. Now, percentile ranking has its own set of issues and problems, but it's an intuitive and I think for parents one of the easiest kinds of scores to understand. So the definition again is the percentage of students in the norm group who scored below a particular raw score. It's your relative performance in the group. So if you're in the 99th percentile, that means that 99% of all of the folks that took that test scored worse than you. And only 1% of the students that took that test scored as well as or better than you. And so sometimes percentile ranks will even be fractionalized out even further, and we'll get something like, you're in the 99.99 percentile, which means that only 1/10 of 1%, 1/100th of 1% of the folks that took the test did as well as or better than you. So percentile rank is, I think, an intuitive score. It's very easy to understand. You can explain it just as quickly as that. There are some issues with it, though. There are a few requirements. First is that we have to have some kind of conversion table. We have to know what one's relative ranking was so that we can go from raw scores to percentile ranks. And when it's on a normalized set of scores, in other words, this is from a standardized test, those percentile ranks actually can be lined up to a z-score, a distribution score, and we can equate them to the percentile ranking on a test like that. Let's say a widely published test like the SAT, or perhaps something like the Stanford tests of achievement. We can equate those percentile ranks directly to a standard score. We can't do that unless it's based on a norm-referenced assessment, something that is linked to the normal distribution. We have to have a norm group and a conversion table that's appropriate for the students taking the test. So we may see the same test with multiple different kinds of comparison groups. For example, there might be a local comparison group where you have one percentile ranking versus the national comparison group. Now, sometimes Maine will get this, so schools will get a percentile ranking of how well they did against all other schools in Maine, and then how well they did against all other schools in the country. And those might be two different percentile ranks. So many different kinds of tests and many different kinds of students and groups means many different kinds of conversion tables. In other words, you have a percentile ranking against each group you're being compared to. There's not just a single one. There are different purposes for these kinds of comparisons, and so we need different kinds of forms. Some of the limitations of percentile ranks, although they're my favorite kind of standard score, if you will, to report. They're actually not a standard score, but they're normalized, converted score to report to parents. We always have to refer to that student's percentile rank as relative to a particular norm group. So simply to say that Billy is in the 99th percentile isn't really terribly descriptive. You have to say he's in the 99th percentile against all other, say, fourth graders in the United States, which is different than saying that he's in the 99th percentile against all other children in his school. Those are two different comparison groups, and so it's very important to be clear about who you're comparing them to. If you're in the 99th percentile against all other doctors in your medical knowledge, that must mean you're pretty talented. But if you're in medical school and you're in the 99th percentile against all people in the population in your medical knowledge, that's probably less of a statement about your real capabilities as a doctor. Because you would presume that you would know more than the vast majority of the population. Since less than 1% of the population are actually medical doctors, you would expect that you should know more than 99% of the population. So it's not really terribly descriptive about what you know. This usually requires multiple sets of norms, especially if you're in high school and beyond. So in other words, you really have to have multiple sets of comparison groups in order to make any kind of reasonable conclusion about percentile ranks. And then finally, and this is the most significant issue with percentile ranks, is that the units are not equal, particularly at the extremes of the distribution. Okay, and so to show you this, I'm going to do another quick kind of demonstration, and you'll get to see more of my great artistic skills. All right, so let's take a look and see if I can do any better job drawing and kind of demonstrating for you what I'm talking about when I say that percentile ranks are not equal interval units, although normalized curve equivalents are. Let's take a look at what that means. So here's our bell-shaped curve again. Here, what we see in each of these parts, we see, of course, the mean right here. And we see this is one standard deviation above, right? Plus 1, plus 2 standard deviations above, plus 3, okay, and plus 4. And in each of these segments, we see the proportion of the population that's represented in that part of the normal distribution. So we expect about 68%, 68.26% are in the plus or minus 1 standard deviation range. Now, that is typically considered the average range. This next segment here is about another 14% of the distribution, and it is between 1 and 2 standard deviations above, and this is typically considered to be sort of the above average. Conversely, of course, there's another 13.5%, and this is the below average segment of the curve, typically. When we think about placing kids into things like special education, this is oftentimes the criteria which is used to determine whether or not a child qualifies. For example, if a child is going to be diagnosed with mental retardation, which is still a category of disability, what we are looking for typically is that they've gotten an IQ test score that is less than 70. Now, when we talk in a moment about standard scores, we're going to talk about the fact that 70 is, in fact, just exactly 2 standard deviations below the mean. Okay, you'll see maybe in a little bit better detail later why. But if you look at your cross-reference chart that I asked you to get out at the very beginning, you'll see that 0 lines up, in fact, with 100 on the standard score scale, and that 70 is, in fact, 1, 2 standard deviations below. So we know that children with mental retardation are in the bottom roughly 2.5% of the population. Conversely, if we look at children who have extremely high IQs, these are typically IQs of 130. That's 100 plus 15 more is 130 or more. So the underlying percentile ranking scale directly corresponds with where your score is relative to the mean. So you'll notice that the mean sits exactly in the center of the distribution, which is exactly the 50th percentile, which is also the 50th normal curve equivalent percentile rank. I'm going to leave the NCE, or the normal curve equivalent, aside for the moment. As we go up, I want you to notice something. Look at how tightly bundled together these percentile ranks are. Okay, so we go from 50 to 60 to 70 to 80, okay, fairly quickly. Why is that? Well, it's related to the shape of the distribution. The majority of people are here in the center. We just said that 68% of the people are here in the middle. That means that only 16% are up here, and then only another 16 roughly percent are down here. And so we move from the 50th percentile to the 60th percentile very quickly because there's lots of people represented here. Okay? The height of this represents the number of people that are at this score level. So the number of people who are right on average is the greatest. And the number of people that are scoring extremely above the mean are very small. It's a very small number of people. So what we see in the underlying percentile ranking is that we move from 50th to 60th to 70th to 80th very quickly because this represents lots of people in a small area longitudinally here. Okay, we don't have to travel very far to the right or very far to the left to represent a lot of different people. Now, when we get further out into the tails of the distribution, way up into these extreme values, notice that we go from the 97.7th percentile, right, all the way to the we go to the 99.9th percentile. That's only 2.2, roughly, percentile ranks between 2 standard deviations and 3 standard deviations. Now compare that. This is the same increase in sort of raw performance, if you will, as is this, from average to 1 standard deviation above. That distance represents the change of 34.13 percentile ranks. So it's much easier for a child to move, say, from the 40th percentile to the 60th percentile. That's 20 percentile ranks higher, okay? But it's only probably about a third of a standard deviation difference in actual scores than it is for a child to move from the we'll say the 84th percentile to, say, the 99th percentile. That's only 15 percentile ranks, but that's 2 whole standard deviation units. So it's not as far as this child moved in percentile ranks, going from the 40th to the 60th. But in order to just go 15 percentile ranks from the 84th to the 99th, they've had to go 2 entire standard deviations of performance. Much more difficult to do. So what's the upshot of this? If you have a child that moves from the 85th percentile to the 98th percentile in 1 year, okay, that's moving from here to here, that represents a really phenomenally large gain. And it's something that you as a teacher should pay a lot of attention to. On the other hand, a child that moves from the 40th percentile, that's right here, to the 60th percentile, that's right here, that's really not a big deal. That's probably about a third of a standard deviation of actual change. It's really, it's good, and you might point it out, but it's not something that you would really pick up on and think was a substantial shift in that child's performance. Okay, so on to the last section, which is about standard scores. And I've actually talked about these in an earlier segment, so you may want to go back if you're having trouble here. Go back to the opening of this section where I talked a little bit about national curve equivalents, or not national curve equivalents, excuse me, but rather t-scores and z-scores. I'm going to talk about them in a narrative fashion here, but you may want to go back to that earlier section and take a look at that piece. So standard scores are how far above or below average a student scored. And it's all measured in standard deviation units, which I've obviously been alluding to this entire time. The mean and the standard deviation are for a particular group, and so we can't necessarily transfer from one to another. However, once we convert them into standard scores, if we're basing them off the same premises, excuse me, we can make some fairly reliable and sound judgments about comparing performance across tests. So, some of the advantages of standard scores. One is that they're based on the normal curve, which means that our scores are distributed symmetrically around the mean, or the average. Each standard deviation represents a fixed but different percentage of the cases. All right, so we know a lot about what it means to go from the second to the third standard deviation because it's based on the theory of the standard distribution, or the normal distribution, where we have fixed percentages, as we saw in the previous slide. The standard deviation allows us to convert very different kinds of raw scores into one common scale that is of equal units and can be readily interpreted in terms of the normal curve. All right? We have to make assumptions, though, that our scores follow a normal curve. All right? And classroom tests that we would normally give generally don't. They're usually a skewed distribution. However, large-scale norm reference tests do follow this pattern, and so we can make a lot of assumptions about how we can interpret those scores. So, standard scores share a common logic. They can all be translated one into another. Okay, so figure 19.2 on page 494 in the 9th edition, I believe, and you can go back to that chart. You should have that out anyway. So the z-score, of course, is the simplest score, and it's the score upon which all others are based. And this is just the expression in standard deviation units. I've covered this pretty thoroughly already, so I'm going to keep going. The t-score, again, is based off the z-score. And instead of like the z-score, where the mean is 0 and the standard deviation is 1, now we're just saying the mean is 50 and the standard deviation is 10. So 0 as a z-score is 50 as a t-score. 1 plus 1 as a z-score is 60 as a t-score. And so on and so on. So we can obtain a t-score from a z-score by just saying its t is 50 plus 10 times z. So you'll see that that always works out, even if z is minus 1. If we say t equals 50 plus 10 times minus 1, that's 50 plus negative 10, which is 40, and voila, we have our transform score. Of our z-score of negative 1 becomes a t-score of 40. Normalized standard scores are a way for us to start with scores that we want to make conform to the normal score. We can get our percentile ranks for each score, again, only if it's based on the normal distribution and the assumptions of normality are correct. So for classroom assessment, this probably wouldn't be true, but for our large-scale things, it is. We can transform all of our percentiles into z-scores using that kind of conversion table. I say that I handed one out in class, but the conversion table I'm talking about is that chart that you have in your book that I pointed you to. When we transform this, we can get any other kind of standard score that we want, knowing that they're all based on the same common z-score. And we have to make sure that our assumptions are right, namely that our scores actually follow the normal curve. And if they don't, all of our interpretations about being above average and below average and to what extent those things are comparable, all of that's undermined if our scores don't follow the normal distribution. So for classroom-based things, this is generally not going to be the case. For large-scale tests, you should be able to make the assumption that this is true. Another reporting format that you might see are stanines. Stanines are not used as commonly now as they were, say, 15 or 20 years ago. They're just a different type of normalized standard score. It's called the standard 9. With each of the different groups from 2 to 8 covers a half of a standard deviation. And then we see that stanine 5 is percentile ranks 40 to 59. That's the middle 20% of the distribution. And the way that these were designed was that a difference of 2 stanines would signal a significant difference. So it was a way to very easily say, oh, well, somebody went from a 6 to an 8, that's a big difference. Somebody went from a 5 down to a 3, that's a big difference. So it was designed to be a quick and easy way, but it's in a different format than other standard scores. Okay, so I'm going to tie this all up here in the next few minutes. This session is looking like it's a little longer than I wanted it to be. So I apologize for that. I've been trying to keep these about 25 minutes, and I can see that this is going to wind up running about 45. The use of standard scores is particularly valuable in examining student profiles of performance. You can compare a student's scores across different kinds of tests and subtests if they all generate standard scores. Now, this is, of course, with a limitation of saying that the norm group by which they're being compared may be slightly different across these tests. But it still gives us a useful benchmark to look at how well is the student doing overall. I say here that all tests must use the same norm group. That's rarely the case, but the same characteristics of the norm group, it's a national sample and so on. We're going to talk about what makes a good norm group here in a moment so that you can better understand how these tests are created and what it is that you want to look for when you think about who your children are being compared to when you look at their scores. We know that by plotting profiles we can see students' relative strengths and weaknesses. So we have a common metric of the standard score or the percentile rank to give us a way to interpret where students' relative strengths and weaknesses might be. One of the things that you want to make sure is that the scores that you see from students are plotted using confidence bands to illustrate the degree of error in each score. Now, as we talked about when we talked about reliability, and we talked about the idea of scores in general, is that a score is not a precise measurement. It's a score within a range of error. When we talked about reliability, we talked about the degree to which a test gave reliable or consistent results. The error band, or the error bars that we sometimes see around children's scores, are just that. These are standard errors of the measure. Now, I'm going to talk about what standard errors are when we talk about the descriptive statistics, so I'm not going to go into that right now. We want to interpret scores as different only when these error bands don't overlap. And for those of you that are confused by that right now, hold on for that next section on descriptive statistics, where I'm going to talk about the use of error bands. Sometimes we could plot these things out by gender or race. It's a controversial practice, I think. It's useful from an instructional point of view to see if we have kind of equity of access for students in different subgroups, but it becomes a little bit problematic if we're going to use those kinds of things to help us build a contingency table to determine, should more boys get into a program or more girls get into a program based on their past performance. So, tests sometimes come with an explanation or a built-in reporting system that provides sort of a narrative around these standard scores, and they give you a frame of reference. I usually don't find that these are particularly helpful for most teachers because they tend to phrase it in extremely technical language that I think is difficult for most folks to really parse. So I wanted to finish up here by giving you some criteria for judging norms. And I'm going to go through these quickly because most of the text is already in the slides. One of the questions should be, is the group that you're comparing to relevant? Is it relevant to the set of decisions that you want to make? And is it relevant for the set of students that you're testing? Is it representative? Does the norm group actually reflect the students that you're testing? For example, if you're working in an inner city school and you're working with, for example, if you're maybe in Lewiston and you're working with a large group of Somali students, how many of the tests that you're choosing actually adequately represent recent immigrants to the U.S. from this part of Africa that have the specific kinds of language and cultural differences that that group of students has? So chances are that most tests don't adequately reflect that particular group of students that they're testing. Therefore, it's very difficult for them to make good, valid assumptions about what students do or don't know based on their test results. Are the norms up to date? For example, the copyright on a test might mean that it's recently been republished, but that doesn't mean that it's had a new norm group sample identified. The SAT used the same norm group for years and years and years, in fact for decades, tracing back to a group of young white men that were college-bound in the 50s when they served as the first norm sample for that test. And they remained the norm sample for that test for a very long time. Beware of the Lake Wobegon effect. If sometimes when we have old norms, we can have everyone seeming to perform above average, which of course is not true. Conversely, of course, the opposite was true with the SAT results. Those white males from the 50s who were college-bound did not reflect the broader cross-section of students who are now headed on to college. And so they had to redo the norms significantly in the 80s to better reflect the current population of students who take the SAT and go on to college. Are the norms comparable? If you want to compare scores on tests with different norm groups, you've got to check the test manual to see how comparable those groups are. Are they all national? Do they include students of color? Do they include students with disabilities? These are all questions that you've got to kind of identify before you can say, well, they were above average on this test, but they were below average on this other test. If you don't know who the norm groups were and whether or not they're comparable, you really can't make statements like that. Do they adequately describe the norms for the test that you're looking at? What was their method of sampling? Who was in the group? The extent to which different kinds of standardized conditions were maintained during the testing sessions? Tests that provide more detail tend to be better. It's not always true. But if folks are playing fast and loose or are being oblique with the information they provide about the norm group, that's often a good case for not using a test. If you don't know who you're being compared to, it's very difficult to feel confident in interpreting the results that you have about students. So, a few cautions and then we'll wrap up. Scores have to be interpreted with a clear knowledge of what that test measures. You can't rely on the title of a test. Because it says it's a test of mathematics achievement, you have to look at the items in the test to know what it actually measures. In light of the other factors that may have affected test performance, things like student attitude that day, cultural background differences, the health of the students, their motivation level, all of these things play a part in the kinds of scores that students get, because we're making a lot of assumptions based on students getting a variety, usually, of selected response items, right or wrong, based on checking or coloring in the right letter. So we have 50 different items. It doesn't take a lot of those items to create a score that is spuriously high or low. I think all of us are wise to really critically look at test results and think about the consistency of them over time. We need to think about them too in terms of what kind of decision we're making. If this is a low-stakes decision, then we can interpret the results and really not be too critical of them. They're just another useful piece of information. But if we are making a higher stakes decision, then we need to have a greater level of certainty about the validity of those test results. For example, placement into special education is a significant decision that is made in schools. And so the testing that's involved is generally fairly rigorous to start with. But then sometimes parents will request a second opinion, and they'll request a second set of testing. And schools sometimes, I think, balk at this, or they think that this is unreasonable. Actually, it's very reasonable, because there are many cases where students get quite different results from a second set of administrations of different kinds of individual achievement tests and IQ tests. We have to think about these as a band of scores and not as a specific value. I mentioned this before, but just because a student gets a 117 as a standard score doesn't necessarily indicate that that's precisely their performance level. No, in fact, we want to talk about it within the standard error of the test. So we'll talk more about that in the descriptive statistics portion. In light of all of the evidence, look for corroborating or conflicting evidence. So do other kinds of test scores, or does the student's performance in class, or does other kinds of observations, do they support or do they confound your conclusions based on your large-scale assessment? And then finally, of course, never rely on a single score to make a big decision. So, thanks for being patient with this very long discussion. And the next section of the course will be around looking at the statistics and some of the basic score characteristics. For example, I mentioned standard errors. We'll also look at things like mean, median, and mode, a little bit more about percentile rank, and that will be a lot shorter segment, be just a quick overview of descriptive statistics.